Okay, can you hear me? Good. So, my name is Javier Pimás, for those who don't know me. I work for Quorum Software. I have been working on Smalltalk VMs for a long time. And today I'm going to present some work which it's a presentation about the work we have been doing on B, but also some ideas that we want to develop. And so this talk is not only to present the ideas, but also to receive feedback about things we can talk later. So I have been working on this concept of live metacircular runtimes, which are basically live virtual machines. So let's move a little forward. This talk has 3 parts. If we have time, we will have a demo in the end. The first part is about the B VM, or the B live metacircular runtime. Second part is going to be about the next thing we are working on. And as I've noticed that we didn't have a Smalltalk in 3 years, I didn't present any news on B for the last 3 years. So I wanted to include a little bit on the progress on that, even though I wanted to talk more about the next ideas. So let's start with some contextualization. We have been working on, we have already 50 years of object-oriented programming, Smalltalk for 50 years, some other languages are even older. And so let's try to think about what were the things that were important when people were researching about Smalltalks, right? So they contacted a lot of people that studied different ways in which we think, right? And so people that came with ideas as constructionism and constructivism, how we learn by constructing concepts in our mind, or how we learn by constructing, as we just saw. So the idea was to develop methods to think better, right? So they came with very interesting new programming languages, right? And so those languages let us treat our domains in a more direct way, with less code, with less complexity. So in the end, we can do better things with them. But what is the problem? Well, still, when we have to make those languages, right, we have to implement some layer that let us transform those high-level languages to low-level languages. And those languages used to implement the high-level languages are still not very high-level, right? So if we see, most popular programming languages, they are still using VMs written in C or C++. And what is the problem that I see with that and that we saw when we were working on B? Well, if you see the amount of complexity that those implementations have is huge, right? So we are talking about hundreds of thousands of lines of code, even millions, right? If we see how V8, which is the JavaScript implementation on top or below Chrome, well, it's almost 2 million lines of code. So they are very complex. They are highly efficient, but they are still very, very complex. And we want to reduce the complexity of that. And why? Because we want to make systems that can evolve and can adapt, right? If we have systems of millions of lines of code, well, it's very hard to adapt to new changes, and it's also impossible to create new things unless basically you have billions of dollars to have teams of hundreds of developers to improve them. So this is a picture of how a traditional virtual machine works for a Smalltalk environment. So you have some meta objects like classes and meta classes. You have the compiler maybe in Smalltalk. You have a lot of things there, but you still have some things that are used from a lower level, which is the VM. So when you want to execute a method, you are going to the interpreter to take the bytecodes and implement the semantics of the language, or to create new objects, things like that, right? So what is the nice thing of Smalltalk? Well, you still have that the meta objects are coded in the environment, but there are still things that are coded outside the environment, and that if you want to change something about the VM, you have to restart. You have to go back to a traditional software development mode. What did we do with B? Basically, we implemented all the remaining parts, which were not that many, in Smalltalk, right? So what do you want? What do you need to take a VM and move it to the Smalltalk world? Well, you have to implement a few pieces, and then after that, you get a system where everything is written in Smalltalk. So, for example, the native code compiler, you can write it in Smalltalk. And what's the advantage? Well, you can program it lively. You can you are going to have less lines of code because it's a higher-level language, and you can implement the whole system like that, and you can get a very reduced system. So B, in particular, is a complete Smalltalk system that is written, or a Smalltalk runtime that is written in less than 5,000 lines of code, right? You have a JIT compiler, you have a garbage collector, everything you would expect from a Smalltalk, you have it, and it's very, very small. And its performance is similar to the one you have in the open Smalltalk VM, right? Okay, and all that can be lib programmed. And, well, so what's next, you might ask. Okay, so this is great, and we have been using this B Smalltalk for our product, shipping it to clients, but we still think about new things that we would like to do. And at some point, we wanted to be able to start from scratch, right? Why? Well, first of all, the desktop was an interim Dynabook, right? So it's not even our final platform. We are used to use Smalltalk in a desktop environment, but if this is not going to be our environment, we should think, well, how do we need to change Smalltalk? So we are using everyday mobile devices. We access software through web browsers, and everything is becoming programmable. I don't know if you saw that. This is un cebador de mate robótico. Okay, so we can program anything we want, right? We just have to think more, and we can find new ways of programming stuff. So we need to start from scratch for being able to program on those platforms. And okay, so what do we need to do? We need to have a minimal system. We need to be able to read some code kernel and to be able to compile it. And with that, we need to be able to execute it. So the idea of what we named Powerlang was just a framework for creating a Smalltalk from the source code, right? And after that, we have some interesting ideas. So the first thing that you need to do if you have a Smalltalk core or a Smalltalk kernel which has all the objects typical in a Smalltalk is you need to create an image, right? And to create an image, you need to bootstrap it. You need to take the source code and create objects that are alive and that you can change, right? So that's what we call bootstrapping. When working on this, there are many ways of bootstrapping a system. We started by creating the objects in another Smalltalk. You take a Smalltalk, you use it to compile methods of your new Smalltalk, and you use it to create new objects there, like a virtual image, right? But then you start having problems with, well, this object is an object here, but I need to use it outside. Or you have to have some way of distinguishing where objects are really living, right? So this metaphor of hosting system and guest system is interesting because basically you have a host where you are going to create objects and you are going to give those objects some kind of liveness, and then you are going to remove some parts of the connections between the objects in the guest and the objects in the host as long as you complete the execution or you complete the creation of the objects in the guest, and so they can be self-sustainable. When you are working with different Smalltalks, like the host, the guest, and maybe the Smalltalk that you are creating is incomplete, so it might be a Smalltalk that doesn't have a user interface or is thought to be used in a robotic platform or things like that. You need to be able to have minimal things, right? And we are not that great in the Smalltalk community, I think, with modules. So we are trying to design a system where we can start from scratch with a small kernel and load stuff on top of that, so that we can get really minimal systems from the beginning and not try to remove stuff when we want to deploy. Instead of that, we want to be doing the converse. So we want to be able to do this kind of requiring where we say this module depends on that other module, we want to use this class, and then we want to create methods that reference those classes. So to be able to do that, we did some small changes to the language. So our Powerlang compiler, it's a bit more lazy than the typical Smalltalk compiler, so when it finds new names, it tries not to bind them. So it only binds temporary and arguments, because these are the most used variables, and it's important to not be very slow. But if it finds any other variable that it can't bind, like a global or like an instance variable or like something else, it basically tries to leave it without linkage, right? So at the moment of execution, it will perform some kind of lookup in the same way that we do lookup with a method dictionary, but this time for variables, right? So it has to have a kind of namespace, and when it does the lookup, it caches the result. So it works in the same way that a method dictionary and a message lookup. And if somebody touches that name, then it has to flash the cache so that afterwards it will find the new name. And with these kind of things, we can create a system where all variables that are not linked can be loaded afterwards, and there's not going to be any problem. Oops. So let's show a little demo of what we have been up to. Let me change one more thing, because I would like to see my screen as in the projector. So. Wow. Okay. Okay, so what do we have here? Basically, we are creating a new system. So we need a working system. We want to develop this all from an open source point of view. So we are using Faro for this. Basically, what we are trying to do is to create a new Smalltalk image on top of the Smalltalk image that is running in Faro. And to do that, we are not going to reuse the VM of Faro, so we have no ties from what Faro does when it executes a method, for example. So we have to do our own lookup, we have to do our own interpretation of bytecodes or whatever. We have to read the specification of a Smalltalk, and then we have to execute it, right? So how does this platform work? We have a specification somewhere. The specification is all made of just files that we have here. We have a kernel. The kernel implements a Smalltalk 80 or something like that kernel set of objects. Each of them are programmed using or written in tunnel format. So what we do from our Faro platform is to load that specification and to create objects of the kernel so that it can start executing. And when we have that working, what we do next is to start evaluating code inside that virtual image with an evaluator that we have here. So we have written a set of different possible evaluators for the intermediate representation of the code. And after we created the kernel objects, we can do basically anything that could be done with any Smalltalk. So what I wanted to show, for example, is how it works to create a new system, right? We don't want to use this forever. We want this just to bootstrap the system, right? So, oops, Faro crashed. Oh. Let's start it again. So, what we want to do is to bootstrap a system, right? So what do we have to do to bootstrap the system? We created the smaller possible set of objects. They are already working there. So we could now write those objects to a file, but we do something a little bit different, which is to send a message to the virtual image, to load a module that will write an image, and that module, in this case, is going to be a module that writes the image in a JSON format so that we can execute that on a JavaScript browser, right? So what do we need to execute on a JavaScript browser? We need basically an evaluator of Smalltalk code written in JavaScript, right? But we already have an evaluator here that is used for initialization of the image and just for letting the new system write itself. So we can transpile that to JavaScript and we can execute that. So we are doing that. All these classes are going to be translated to JavaScript. Sorry. And we have here an interpreter that, if you have a look, each of these classes that seems pretty normal in JavaScript are actually JavaScript code generated from the evaluator written in Smalltalk. So we have now a Smalltalk evaluator written in JavaScript. We didn't write it manually, we created it. And our module that has to write some JSON is around here. So we have a module. We have a module writer, and basically what this uses is what it does is to take the image and start looking at all the objects that are there and starts writing them, but using a particular writer, which is a JSON writer. So instead of writing, for example, what we have in the typical image, which is a binary image, it starts creating a JSON file where each object is represented by an array. Each reference to another object is basically an offset in an index. An index in an object table, and then some JavaScript code can load that. So if we see, if we go back here, we can see the result. So this is the result of writing the kernel. Each of these is an object. Well, not in the way we are used to see them, but each of them is an object. It has a type, and then it has some references to other objects. Some JavaScript code is going to load it. In the end of the file, we have some kind of export. So the index 400 is for the class message and things like that. So we have everything there. And then we have some bootstrapper that is able to read that JSON file, create the objects in JavaScript, and just use the interpreter to interpret that code. So what we have finally for the demo, so we can run this and check that it works. Yeah, it's working. Okay, so what are those tests, for example? Okay, so what do these tests do? Basically, they send some simple messages like, let's see, okay, they create a small integer and check that it's okay, but then at some point send yourself to nil. So they load the kernel, they send the message yourself. It's named send local because yourself here is a JavaScript string, and it sends the message yourself to nil object, and then it asserts that the result is still nil object. And we can do that for different things, testing 3+4 or doing some more complex computations. So you can calculate Fibonacci or things like that. And well, basically what you have is a platform that can now run on top of JavaScript in any browser. So you have a Smalltalk that can run in any browser if you create an object which is modular and you implement it the way we are trying to do. So this is just one implementation, right, of an evaluator. We also have plans for porting our JIT compiler so that we can also use a traditional VM with this same Smalltalk. So the idea is that we can have different VMs for different platforms, and so this PowerLang project is a kind of Smalltalk enabler platform. And well, that's it. So thank you for listening. Yes.
This is something you need for the bootstrapper because you are transforming in
Yeah.
this way, or?
Well, it's something that helps because when you start compiling code, you start to discover that you need things that are usually not part of your system anymore if you are bootstrapping, right? Or maybe they are partially. What, for example, if you want to compile a class that you don't have the superclass because it's another module that you didn't load. And maybe you don't want to load that module yet because you don't really know what the superclass is going to be. It has a name, right? But maybe you want to, for example, create a module where you have a version of the module and you have another version of the module, right? And in the other version of the module, the superclass has the same name, but it's different, right? So maybe the instance variables are different. So you might want to be able to load both at the same time, right? So the idea to have late bound names is to allow for that kind of behavior. You can also load the module and not know what a global is and expect that to be loaded later. Or maybe if the global is not found, then you can trigger some kind of does not understand, but instead of does not understand, you can have a not found message. So you can react to that not found and load lazily another module. So I think those things are most useful if you are working with minimal systems where you still don't know what you are going to need. And that's the idea.
Yeah, my question is because what usually can easily see the advantage of that, you have a big system.
Yeah.
But you're using the same idea when you are bootstrapping the system. So you have something minimal and you are building.
Yeah, but I think that you still need it because when you start compiling code, for example, for the bootstrapper, maybe if you have to compile the whole system, you don't still have all the classes put together when you are starting, right? So it's easier for the compiler to say, I don't know what this is. Maybe it will be figured out later when we are in the final stage of bootstrapping.
You mentioned that this idea of running this model in a cell phone, in a browser. Is there the possibility of the future to choose certain part of what we implemented in a usual virtual machine, rip it off to a small virtual machine that can run faster in a web browser, in a cell phone? Are you oriented in that direction?
What do you mean by run faster in a browser?
Well, I try to run, for instance, Swiss in a browser with a Swiss
Mhm.
Was
Very slow.
very slow. And maybe if I have a smaller image, a small set of previews,
Yeah.
something more could run a little better.
Yeah, well, there are ideas towards that direction. Actually, I sent a paper to the workshop that present the ideas that are here in this second part. During the presentation of that work, I will show more on that. And yes, basically, my idea is that we can write an evaluator in a high-level language like Smalltalk. We can transpile that to JavaScript, and we can let the JIT compiler on the underlying platform to perform all the hard work, right? So, for instance, V8 has a lot of compilation stages and optimizations and things that can allow your code to run a lot faster than JavaScript if it were interpreted, right? So if you help it a little bit, then you can let it run your code much faster. And there are ways to do that. If you have an evaluator that, like we have here, you can, for example, perform the lookup, right? And perform the inline caching yourself for Smalltalk, because a JavaScript browser doesn't know how to optimize Smalltalk lookup. It knows how to optimize JavaScript lookup, right? So if you optimize the Smalltalk lookup and then let it run, so you are implementing an inline caching on a high level, and then it will implement another inline caching on the lower level for JavaScript code, and you can do more. You can then inline your own message sense. You can inline parts of your intermediate representation, your bytecodes or whatever, as JavaScript code through eval. And there are many ways to optimize code. So this that we show is around more or less the same speed that Amber Smalltalk. It's not very fast. It's like maybe 400 times slower than what we have in B or in Open Smalltalk. But still, it has some benefits, which is it's very small. And we have done some tests to implement those things that I just mentioned, and we got some kind of 10x improvement, so it's still faster. There are other ways to implement a VM on top of JavaScript that are fast, like the one they use in Newspeak. This is a full-blown, let's say, Smalltalk-ish VM that they use mscripten to translate to fast JavaScript, right? So like native code. The problem with that kind of approach is that you have to implement the whole VM. If your VM is slow, you translate it to fast JavaScript, a slow VM, so it's still slow.